Hey folks, this video is going to be an introduction to RC circuits, and no, it's not remote control like a car. RC is resistive capacitive circuits. Okay, and we're going to start with a real simple circuit. So let's say you have yourself a battery, and it's got an EMF, okay, which is a voltage, right? And we hook that battery up to a capacitor, C, okay? And no matter what circuit you have, it's going to have some resistance, so we'll call that R. And then we're going to have a switch, okay? And what we're going to do at time equals 0, we're going to close the switch, okay? So current can flow. And we're going to pretend positives are flowing, just keep it simple. Now, what's going to happen is the capacitor will charge up, okay? So positives, you can think of it as positives flowing this way. So this end of the capacitor will be positive, which would knock positives off the right-hand plate, which will make that negative, and then the positives will continue flowing, okay? The charges will continue flowing until the capacitor is fully charged, and we'll talk about, well, when does that happen or what does that mean in a moment. So before we're going to find the current and charge as a function of time on that capacitor. It takes time to charge up. Now, before we do that, though, we're going to talk about what happens when you first close the switch. So this will be at t equals 0 at the moment you close the switch. And then we're going to talk about when time is really, really big. Okay, after a long time, what happens? Okay, so when you first close the switch, the capacitor, well, charges are accumulating on the left plate, and the positives are being knocked off the right plate. Now, again, it's really electrons going the other way, but let's pretend it's positives. All right, so imagine that you put the first positive on there, and then that first positive on the right side gets knocked off the plate. So that took almost no effort. In other words, at t equals 0, when you first close the switch, the capacitor, it almost behaves like a wire. It's as if charges just run across from one plate to the other. Now, that's not what actually happens, but it's as if that happens. Okay, so the capacitor behaves like a wire. The starting charge, the charge at 0 seconds, is 0. You haven't charged it up yet. Okay, the current at 0 seconds, well, if the capacitor is behaving like a wire, then the current will just be voltage over resistance, which would be E over R. Okay, so that would be your current when you first close the switch. Okay, now what about after a long, long time? Well, charge will build up on this capacitor, okay, until its voltage is equal to that of the battery, but opposite direction, right? For the battery, this is the plus, this is the minus, so it's like clockwise. For the capacitor, it's the opposite, it's counterclockwise. So the charge after a long, long time will just be capacitance times voltage, which would be the voltage of the battery, CE. Okay. So again, we're using our two laws, V equals IR, and we're using Q equals CV, okay, when we're just talking about that. Now, what about the current after a long, long time? Well, after a long, long time, when the capacitor is fully charged, current's going to stop flowing. So the current will be 0. In other words, the capacitor behaves like basically what it is. It's an open circuit. Okay, there's a gap there. So after a long time, things are going to behave like what they are. It's an open circuit. The other way to think about that is it's going to behave like a battery. Okay, so it's going to behave like a battery, but pointed in the other direction, so a negative E. It's going to when it's fully charged, its voltage will be the same magnitude but opposite direction as the voltage of the battery. So on an AP exam, for instance, if you can do that, you're halfway done with the problem. Okay, so now the question is, how about those in-between times? What about between 0 and infinity? Okay, well, then we got to do some math. So in order to do this math, we're going to start with Kirchhoff's loop rule. We know that the net change in voltage around a closed loop is 0. Okay, so if I start here and go clockwise, what do we have? Well, we have the battery voltage, that's E. And then we're going to have the voltage of the capacitor, that's going to be a drop. Okay, if you go from the plus side to the minus side of the capacitor, you're losing voltage. and then you're going to have the voltage drop of the resistor. When current goes to the resistor, you lose voltage. And then you're back to where you started, so that's got to be 0. Okay. Now we got some formulas to put in here. Voltage of a capacitor is Q over C, and voltage of a resistor is IR. Okay, now we've got two variables here. We have Q and I, but they're related. We know that I is the rate of change of Q. So you can rewrite this as Q over C minus dQ dt times R equals 0. Now, this is a special kind of equation. You have something and its derivative in the same equation. This is a differential equation. And you have something in its first derivative, so it is a first order differential equation. Okay. So in order to solve a first order differential equation, there's several ways to do it, but the way we're going to talk about is we're going to separate the variables. You have two things. You have Q and you have time. Okay, so we got to get the Q's on one side of the equation, the dt on the other side of the equation. So, if you do some algebra here, I'm going to multiply everything by C. So you get EC minus Q minus dQ dt times RC equals 0, right? And then basically, if you get the dt by itself, okay, or dt divided by RC. So, if you got EC minus Q equals dQ over dt times RC, okay? And let's see, if you flip everything over, okay, so this becomes 1 over this becomes dt over dq, this becomes 1 over RC, and then you multiply both sides by dq, you would end up with the following. On one side, you would have a dt over RC. On the other side, you have a dq over EC minus Q. So now we've separated our variables. We have t on one side, we have q on the other. And now we're going to integrate. Okay, the left side, the time goes from 0 to any time later that we're interested in. For the right side, the charge started off at 0, and then we want to know the charge at some point later. So we'll call that just Q, the charge at some other point in time, okay, or Q as a function of time. You can even put that there, okay. All right, so the left side of our equation just becomes time over RC evaluated from 0 to t. How about the right side of our equation? Well, what you're basically integrating is 1 over negative x. It's 1 over negative q. The integral of negative 1 over x is negative natural log of x. So instead of negative natural log of x, though, we have negative natural log of EC minus q. And here's one of the most important things. You have to evaluate this. Okay, the 0 actually going to matter here, right? All right, so the left side of our equation, that's really simple. T over RC. The right side of our equation, you get negative natural log of EC minus Q minus negative natural log of EC minus 0. Okay. Now, if you don't put that 0 in there in the right spot, then you're going to get a total nonsense answer. Okay. Do a little more algebra here. So T over RC equals, you end up with natural log of, now we're going to use our log rule. So this becomes positive. So you got natural log of EC minus natural log of EC minus Q, which becomes natural log of EC over EC minus Q. Okay. And we want to determine Q. We want to solve this for Q and get Q by itself. Okay. So we have to take the exponent of both sides. You have a negative in here, so you have to be careful. Okay, so what's that going to look like? So you get e to the t over RC, okay, equals EC over EC minus Q. Okay, and we want to get Q by itself. Okay, so I'll kind of work over here now. So you end up with EC minus Q. I'm going to move this to the left side. I'm going to move this to the right side. So you get EC over e to the t over RC, which becomes EC times e to the negative t over RC, if you get rid of that fraction there. So we got this equals this. We're trying to get Q by itself. If you get Q by itself, you get the following. You get EC minus EC times e to the negative t over RC, or if I factor out the EC there, Q equals EC times 1 minus e to the negative t over RC. That is charge on the capacitor as a function of time. Okay. Now, some things to think about here. Does this equation actually hold for this condition? At 0 seconds, does Q equal 0? At a long time, does Q equal CE? Well, let's check that out. If I plug in time equals 0, e to the 0 is 1. 1 minus 1 is 0, and Q is 0. So at 0 seconds, Q is 0. After a long, long time, e to the negative big, big number is basically 0. 1 minus 0 is 1. Q after a long time equals EC times 1, which is EC. So we get the conditions that we should get. Now, some other things to note here. Oftentimes, we'll call this Q max. That's the maximum charge. Okay. The other thing that's really important is RC. We call that the time constant. The units on that got to be seconds, by the way. If you take ohms times farads and you do some work with that, you'll end up getting seconds. We call that the time constant. We give it a capital T. So tau equals RC. Your time constant equals RC. And it's a measure of how fast your circuit is. The bigger RC is, the longer it takes to fully charge your capacitor. Okay, so that's called the time constant. So another way you can write this is you can write Q as a function of time equals sum Q max times 1 minus e to the negative t over tau. And students will typically memorize that tau equals RC. It's something that's exceptionally important to kind of know all the time. You're going to use it a lot. Now, in our next video, we will talk about the current here, and we'll see where these answers come from and how to get there. But this is the charge on a simple 1R, 1C circuit as the capacitor charges up. So I hope that video was helpful, and thank you very much.